If you like the space and learn about its curiosities, subscribing to the channel. Thank you for your attention and enjoy the video. What is space-time? Imagine a vast, invisible stage stretching endlessly in every direction, hosting every star, planet, and galaxy in existence. This stage isn't just a backdrop, but an active participant in the cosmic dance. This is space-time, a concept so fundamental that it redefines how we perceive the universe. To understand space-time is to step beyond the ordinary and grasp a reality where time and space are intertwined in ways that challenge our instincts. At its core, space-time is a fusion of two ideas that seem separate in everyday life: space and time. We think of space as the three-dimensional area around us: length, width, and height, while time ticks forward like the steady beat of a drum. But Einstein's groundbreaking insights in the early 20th century revealed a deeper truth. Space and time are not separate. They are part of a single, four-dimensional continuum. This union forms the fabric of the universe itself, a flexible medium that responds to the presence of matter and energy. How can we picture something as abstract as space-time? Imagine a stretched rubber sheet. If the sheet represents space-time, then objects like planets and stars are weights placed on it, causing it to bend and dip. The heavier the object, the deeper the indentation. This visualization, though simplified, helps convey an extraordinary reality. Space-time can bend, stretch, and even ripple. Now, what makes space-time truly mind-bending is its role as the stage for everything that happens in the cosmos. It's not just a passive backdrop, but a dynamic entity that shapes the motion of celestial bodies, the path of light, and the flow of time itself. This idea reshaped physics, dismantling long-held notions of a rigid, unchanging universe. Why does space-time matter to us? It's more than just a theoretical curiosity. The GPS in your phone wouldn't work without accounting for the curvature of space-time around Earth. Satellites orbiting high above the planet experience slightly weaker gravity, causing their clocks to tick faster than those on the ground. Einstein's equations, describing the bending of space-time, allow engineers to correct these discrepancies, ensuring precise navigation. The fusion of space and time also opens the door to questions that border on the philosophical. If space and time are two sides of the same coin, what does that mean for concepts like the past, present, and future? Does the fabric of space-time encode the history of the cosmos, like grooves on a record? Delving into the nature of space-time is like peeling back the layers of a cosmic onion. Each layer reveals deeper mysteries, from the smooth stretching of the cosmos to the violent warps created by black holes. These distortions are not just academic. They are integral to understanding phenomena like gravity, light, and the ultimate structure of the universe. At this point, you might wonder, how do we know this four-dimensional reality exists if we can't see it? The answer lies in experiments and observations. From the bending of starlight during a solar eclipse to the detection of gravitational waves rippling through the cosmos, evidence for the nature of space-time surrounds us. Each discovery adds to the tapestry of understanding, painting a picture of a universe far stranger and more interconnected than we could have imagined. Space-time is more than an abstract concept. It's the key to unlocking some of the greatest mysteries of existence. It provides the framework for everything we observe and the answers to questions we haven't even thought to ask. With every step we take into the unknown, space-time remains our guide, shaping our understanding of the cosmos and our place within it. If you've ever rolled a marble across a stretched sheet of fabric, you might have noticed how a heavier object, like a ball, creates a dip that redirects the marble's path. Now, imagine that instead of fabric, the sheet is space-time itself, and instead of a ball, you place a massive star or planet on it. This simple analogy captures a profound truth. Gravity is not an invisible force pulling objects together, but the result of curved space-time guiding the motion of everything within it. This revolutionary idea, introduced by Albert Einstein, replaced the Newtonian notion of gravity as a force acting at a distance. Einstein proposed that massive objects distort the very fabric of space and time around them. Imagine the Earth sitting on this cosmic fabric, creating a depression that bends the trajectories of other objects, from satellites in orbit to meteors hurtling through space. This bending is what we perceive as gravitational attraction. But how does this work? To grasp the mechanics of space-time curvature, it's essential to consider a critical principle of Einstein's theory of general relativity. Mass and energy tell space-time how to curve, and curved space-time tells matter how to move. In simpler terms, the presence of mass or energy changes the shape of space-time, while the curved space-time dictates the paths objects take. Consider a scenario. A beam of light passes near a massive object like the sun. In a straight-line world, the light should travel undisturbed. However, in a universe governed by Einstein's laws, the sun's immense mass curves the space-time around it, and the light follows this curvature. This bending of light, known as gravitational lensing, has been observed and confirmed in numerous astronomical phenomena, from the deflection of starlight during a solar eclipse to the dramatic arcs of light seen in deep space images of galaxy clusters. To visualize this in a more terrestrial sense, imagine walking across a field with a gentle slope. Without thinking, you naturally adjust your path to account for the incline. Similarly, in curved space-time, objects adjust their motion, not because they are being pulled by a force, but because the geometry of space-time directs them. Now let's scale this concept up to celestial proportions. The Earth orbits the Sun not because the Sun pulls on it with an invisible rope of gravity, but because the Sun creates a massive dimple in the fabric of space-time. The Earth, moving through this curved space-time, naturally follows the bend, tracing an elliptical path. This phenomenon isn't limited to planets. Everything from the smallest asteroid to the largest galaxy cluster dances to the tune of curved space-time. The beauty of space-time curvature lies in its universality. It applies not just to massive celestial bodies but also to everyday phenomena. For instance, if you drop a ball, it falls toward the ground because Earth's mass curves the space-time around it. On a much grander scale, black holes, regions of space with gravity so intense that even light cannot escape, represent extreme examples of this curvature. Near a black hole, space-time warps so severely that it behaves almost like a waterfall, pulling everything inexorably toward its center. Einstein's theory not only explains gravity in terms of space-time curvature, but also predicts phenomena that would otherwise seem fantastical. One such prediction is gravitational time dilation, the slowing of time in stronger gravitational fields. For example, a clock closer to the surface of a massive planet will tick more slowly than one further away. This effect, while subtle, is measurable and must be accounted for in technologies like GPS, which rely on precise timing. Gravitational waves, ripples in space-time produced by cataclysmic events like black hole mergers, offer another stunning confirmation of Einstein's ideas. These waves propagate outward at the speed of light, subtly stretching and compressing space-time as they pass. Detected for the first time in 2015, gravitational waves not only validate the concept of space-time curvature, but also open a new window for exploring the universe. But here's a tantalizing question. If space-time is curved by mass and energy, could we ever manipulate it ourselves? While this remains the realm of science fiction, ideas like warp drives and artificial gravity hinge on our ability to shape space-time intentionally. The bending of space-time by gravity is not just a theory. It's a reality that we experience in countless ways, from the motion of galaxies to the simple act of dropping an object. By understanding how gravity warps the universe, we gain deeper insight into the interconnectedness of space, time, and matter. This knowledge transforms our perception of reality, showing us that we are not merely observers of the cosmos but active participants in its intricate geometry. Albert Einstein's revolutionary insight into the nature of the universe shattered centuries of established thought. The concept of gravity as a force pulling objects together, as described by Newton, seemed intuitive. However, Einstein looked beyond this simplicity and asked a daring question. What if gravity isn't a force at all but the result of space and time bending in response to the presence of mass and energy? This question laid the foundation for his general theory of relativity, a framework that would redefine physics and our understanding of the cosmos. To grasp the essence of this idea, imagine standing on a trampoline. If no one else is there, the surface remains flat. But as soon as you step onto it, the fabric sags under your weight. Now roll a small ball across the trampoline. Instead of moving in a straight line, the ball curves around the indentation you've created. In Einstein's view, this is how gravity works. Massive objects like planets and stars distort the fabric of space-time, and other objects move along the curves and dips created by this distortion. Einstein's brilliance lay in translating this simple analogy into a set of mathematical equations capable of predicting the behavior of the universe on the grandest scales. His field equations describe how mass and energy influence the curvature of space-time, and in turn, how this curvature dictates the motion of objects within it. These equations are not merely theoretical. They've been tested and validated repeatedly, from the movement of planets to the bending of light around distant galaxies. One of the most striking predictions of Einstein's theory is that time itself is not constant. In a universe where space and time are interwoven, time flows differently depending on the strength of the gravitational field. Near a massive object, time slows down relative to regions of weaker gravity. This phenomenon, known as gravitational time dilation, is more than an abstract idea. It has practical implications. The clocks on GPS satellites, for instance, run slightly faster than those on Earth because they are further from our planet's gravitational well. Engineers must account for this difference to ensure accurate navigation. Another groundbreaking insight from Einstein's work is the realization that light, though massless, is affected by gravity. When light passes near a massive object like the Sun, its path bends as it travels through the curved space-time around the star. This effect, called gravitational lensing, was first observed during a solar eclipse in 1919, providing dramatic confirmation of Einstein's theory. Today, gravitational lensing is an essential tool for astronomers studying distant galaxies and dark matter. Einstein's theory also led to the prediction of black holes, regions where space-time curvature becomes so extreme that nothing, not even light, can escape. For decades, black holes were considered purely theoretical, but modern observations have confirmed their existence. From detecting X-rays emitted by matter spiraling into black holes to capturing the first-ever image of a black hole shadow, these cosmic phenomena showcase the extraordinary reach of Einstein's ideas. Perhaps the most awe-inspiring consequence of Einstein's equations is the prediction of gravitational waves. These ripples in space-time, caused by violent events such as the collision of black holes, were first detected in 2015. The faint echoes of these cosmic cataclysms travel across billions of light years, carrying with them information about the most extreme events in the universe. Gravitational wave astronomy is now a burgeoning field, offering insights into phenomena that were once beyond our reach. What makes Einstein's insights so profound is their ability to connect the smallest scales of physics to the vast expanses of the cosmos. His equations describe not just how the planets orbit the Sun, but also how galaxies interact, how the universe expands, and how time and space themselves evolve. Yet, for all its successes, the theory also raises questions that remain unanswered. For instance, how does general relativity reconcile with quantum mechanics, the framework that governs the microscopic world? This tension has spurred some of the most ambitious scientific endeavors, from string theory to quantum gravity research. Einstein's vision was not just about equations or celestial mechanics. It was about understanding the universe as a coherent whole. His work has inspired generations of scientists to think beyond the boundaries of conventional wisdom and to explore the interconnectedness of all things. The beauty of his theory lies in its elegance and simplicity, even as it reveals a universe of staggering complexity. Space-time curvature might seem like a concept reserved for astrophysicists, but its effects are far closer to home than most people realize. From the precision of your GPS device to the phenomena we observe in the sky, the bending of space-time influences our daily lives in ways that are both surprising and profound. While we may not notice it directly, this invisible warp in the fabric of reality is a quiet participant in our every move. One of the most relatable examples of space-time curvature comes from the navigation systems we use every day. GPS satellites orbiting Earth rely on highly accurate atomic clocks to provide precise location data. However, These clocks tick faster than those on the ground because they are further from Earth's gravitational pull, where space-time is less curved. This time discrepancy, predicted by Einstein's theory, is small, only microseconds per day, but significant enough to throw off GPS calculations by several kilometers. Engineers must constantly adjust the satellite data using equations from general relativity to ensure your phone can guide you to your destination with pinpoint accuracy. Another fascinating instance of space-time curvature is visible in the phenomenon of gravitational lensing. When light from a distant star or galaxy passes near a massive object, such as a black hole or galaxy cluster, the object's gravity bends the light, creating a lens-like effect. Astronomers can observe multiple images of the same distant galaxy or witness light forming arcs and halos. These cosmic distortions not only confirm Einstein's predictions, but also allow scientists to map invisible structures, like dark matter, by studying how they bend light. Closer to home, the motion of celestial bodies offers a tangible demonstration of curved space-time. The orbits of planets around the Sun, for example, are a direct result of the Sun's mass creating a dip in space-time. Earth follows this curve like a marble spiraling around the indentation in a rubber sheet. This curved path isn't just theoretical, it's observable and measurable, guiding everything from planetary alignments to seasonal changes. Even time itself, something we often take for granted, behaves differently depending on the curvature of space-time. Astronauts aboard the International Space Station, for instance, experience time slightly faster than people on Earth because they are further from the planet's gravitational well. This effect, though imperceptible in daily life, becomes critical in scientific experiments and space exploration, where precise timing is essential. Consider also the way space-time curvature plays a role in natural phenomena like tides. While we often attribute tides to the moon's gravitational pull, what's really happening is a result of the moon and Earth warping space-time around them. The interaction between these distortions stretches Earth's oceans, causing the rhythmic rise and fall of the tides. On an even more dramatic scale, space-time curvature is responsible for some of the most spectacular cosmic events we observe. Gravitational waves, ripples in space-time caused by massive objects in motion, are one such example. These waves, first detected by the LIGO Observatory, originate from cataclysmic events like black hole mergers. When they pass through Earth, they stretch and compress space-time ever so slightly, a phenomenon so subtle that it requires incredibly sensitive instruments to detect. Yet these waves carry with them stories of violent collisions billions of light years away, linking us to the farthest reaches of the universe. The influence of space-time curvature extends even to the behavior of light. Have you ever noticed the way stars appear to twinkle? While atmospheric turbulence plays a role, another factor is the bending of light as it travels through the curved space-time created by massive objects along its path. This bending distorts the light's journey, adding to the visual dance we see in the night sky. These everyday examples are just the beginning. The more we delve into the practical consequences of space-time curvature, the more we realize how deeply it shapes our reality. It's not just an abstract concept confined to theoretical physics. It's a fundamental aspect of the universe that touches everything from the vast cosmos to the devices in our hands. Light, the fastest traveler in the universe, interacts with space-time in ways that reveal its deepest secrets. While we often imagine light moving in perfectly straight lines, its journey is anything but straightforward when influenced by the curvature of space-time. This interaction between light and the warped geometry of the universe gives rise to some of the most mesmerizing and critical phenomena in modern astrophysics. To understand how light behaves in curved space-time, consider this. When a beam of light passes near a massive object, like a star or a black hole, it follows the contours of the curved space-time around it. This bending of light, predicted by Einstein's general theory of relativity, is a direct consequence of how gravity warps the fabric of the universe. But this bending isn't an arbitrary phenomenon. It's a precise interaction governed by the distribution of mass and energy in space-time. One of the most vivid demonstrations of this is gravitational lensing, where light from a distant source is bent around a massive object, such as a galaxy cluster, positioned between the source and the observer. This effect can magnify and distort the appearance of the background source, often producing arcs, rings, or even multiple images of the same object. Known as Einstein rings, these structures provide astronomers with powerful tools to study both the distant universe and the invisible matter, like dark matter, that contributes to space-time curvature. Gravitational lensing is more than just a visual marvel. It serves as a cosmic magnifying glass, allowing us to peer into regions of space that would otherwise remain hidden. By analyzing the patterns of bent light, scientists can infer the mass distribution of lensing objects, revealing the presence of dark matter. Additionally, this phenomenon enables astronomers to detect exoplanets and study the large-scale structure of the universe. Light's interaction with space-time isn't limited to bending. In extreme gravitational environments, such as near black holes, the behavior of light becomes even more dramatic. A photon venturing close to a black hole experiences an intense warping of space-time. If it passes just outside the event horizon, the boundary beyond which nothing can escape, the light can be trapped in orbit, circling the black hole indefinitely. This creates what is known as the photon sphere, a region where light dances precariously on the edge of oblivion. Beyond the photon sphere, light can escape the black hole's grasp but emerges stretched and redshifted, a phenomenon called gravitational redshift. This occurs because the intense gravity of the black hole saps energy from the light, lengthening its wavelength. Observing this redshift provides astronomers with critical information about the properties of the black hole and its surroundings. The interaction between light and curved spacetime also explains why the universe itself looks the way it does. Have you ever wondered why the night sky is filled with stars rather than being uniformly bright? The curvature of spacetime influences the distribution of light on cosmic scales, contributing to phenomena like the cosmic microwave background radiation, the faint afterglow of the Big Bang. This ancient light, stretched by the expansion of space-time over billions of years, offers a glimpse into the early universe and its evolving geometry. Even closer to home, the bending of light by Earth's atmosphere and gravitational field affects how we perceive celestial objects. For instance, the sun appears slightly higher in the sky than it actually is during sunrise and sunset, thanks to the bending of light as it travels through the curved spacetime near our planet. This subtle distortion, imperceptible in everyday life, becomes significant in precise astronomical observations. The role of light in curved spacetime also underscores the interconnectedness of the universe. The same principles that explain why light bends around a galaxy cluster also govern the motion of planets, the behavior of black holes, and the ripples of gravitational waves. This unity of nature, rooted in Einstein's equations, reflects the profound elegance of the cosmos. In understanding how light interacts with curved spacetime, we unlock a key to exploring the universe. From unveiling hidden galaxies to measuring the expansion of the cosmos, light serves as both a messenger and a witness to the dynamic geometry of spacetime. Its journey through the warped fabric of the universe reminds us that the cosmos is not just a backdrop for celestial events. It is an active, living stage where the drama of existence unfolds. Black holes are the ultimate sculptors of spacetime, creating regions where the fabric of the universe is stretched, twisted, and warped to extremes. These cosmic enigmas, formed from the remnants of massive stars, challenge our understanding of physics and reveal the profound power of gravity to reshape reality itself. A black hole begins its life when a star many times the mass of the Sun exhausts its nuclear fuel. Without the outward pressure of fusion to counteract gravity, the star's core collapses under its own immense weight. If the collapsing core is sufficiently massive, it forms a singularity, a point of infinite density where the known laws of physics break down. Surrounding the singularity is the event horizon, the boundary beyond which nothing, not even light, can escape the black hole's gravitational pull. The event horizon is a defining feature of black holes, marking the point where space-time curvature becomes so severe that escape becomes impossible. To an outside observer, an object falling into a black hole appears to slow down as it approaches the event horizon, its light becoming increasingly redshifted until it fades entirely. This phenomenon, predicted by Einstein's equations, results from the way gravity dilates time and stretches light near the event horizon. What lies beyond the event horizon remains one of the greatest mysteries of modern physics. The singularity at a black hole's core is thought to be a region of infinite density, where space-time curvature becomes infinite. Here, the known laws of physics, including Einstein's general relativity, cease to function, leaving scientists with a tantalizing gap in understanding. Bridging this gap requires a theory of quantum gravity, a yet-to-be-discovered framework that reconciles the quantum world with the warping of space-time. Black holes come in various sizes, from stellar mass black holes, formed from collapsing stars, to supermassive black holes, which reside at the centers of galaxies. These supermassive black holes, millions to billions of times the mass of the Sun, shape the dynamics of their host galaxies. Observations of stars orbiting the supermassive black hole at the center of our Milky Way, known as Sagittarius A*, provide direct evidence of its existence and offer a glimpse into its immense gravitational influence. Perhaps the most dramatic interaction involving black holes is their ability to merge. When two black holes spiral toward each other, they create ripples in space-time called gravitational waves. These waves, first detected in 2015, carry energy away from the merging black holes and can be observed billions of light-years away. The detection of gravitational waves has opened a new frontier in astronomy, allowing scientists to study black holes not just as static objects, but as dynamic participants in cosmic events. Black holes also interact with their surroundings in ways that produce some of the brightest phenomena in the universe. When matter falls toward a black hole, it forms an accretion disk, a swirling, superheated ring of gas and dust. Friction within the disk generates intense radiation, often outshining entire galaxies. Jets of material, accelerated by the black hole's magnetic fields, can shoot out at nearly the speed of light, creating spectacular phenomena known as quasars. Despite their reputation as cosmic destroyers, black holes play a critical role in shaping the universe. Their immense gravitational pull influences the formation of galaxies, the distribution of stars, and even the paths of light across vast distances. By studying black holes, scientists gain insights into the fundamental nature of gravity, space, and time. The extremes of black holes also inspire questions about the limits of space-time. Could black holes serve as gateways to other universes, or as conduits for wormholes? While these ideas remain speculative, they highlight the profound curiosity that black holes ignite in our quest to understand the cosmos. Black holes stand as testaments to the power of gravity and the malleability of space-time. They remind us that the universe is far stranger and more complex than our everyday experiences suggest. By exploring these cosmic phenomena, we not only unravel the mysteries of black holes, but also deepen our understanding of the fundamental forces that shape reality. Gravitational waves are among the most remarkable phenomena in the universe, ripples in the fabric of space-time that carry the echoes of cataclysmic cosmic events. Predicted by Einstein over a century ago as part of his general theory of relativity, these waves were once considered purely theoretical. Yet in 2015, humanity finally detected their faint whispers, forever changing our understanding of the cosmos. To grasp what gravitational waves are, imagine tossing a stone into a still pond. The impact creates ripples that spread outward, carrying energy across the water's surface. In a similar way, gravitational waves are disturbances in space-time generated by massive objects in motion. These waves radiate outward at the speed of light, altering the distances between objects as they pass. However, the changes they induce are incredibly subtle, stretching and compressing space-time by amounts smaller than the width of an atom. The most common sources of gravitational waves are violent cosmic events involving massive, dense objects like black holes and neutron stars. When two such objects orbit each other, their immense gravitational pull generates waves that ripple through the universe. As the objects spiral closer together, the waves grow stronger and more frequent, culminating in a dramatic burst when they merge. These mergers release staggering amounts of energy, equivalent to several solar masses converted directly into gravitational waves in mere seconds. The first direct detection of gravitational waves came from the merger of two black holes approximately 1.3 billion light-years away. The Laser Interferometer Gravitational Wave Observatory, LIGO, a groundbreaking instrument designed to measure minuscule changes in spacetime, captured this historic signal. LIGO operates by splitting a laser beam and sending it down two perpendicular arms, each several kilometers long. When a gravitational wave passes through, it causes one arm to stretch and the other to compress, creating a measurable interference pattern in the returning light. This discovery not only confirmed Einstein's predictions, but also opened a new window into the universe. Unlike light or other forms of electromagnetic radiation, gravitational waves are unaffected by dust or gas, allowing them to carry pristine information from their sources. Through these waves, scientists can study regions of the cosmos that are otherwise invisible, such as the interiors of black hole collisions. Gravitational wave astronomy has since grown into a vibrant field. Observatories like LIGO and its European counterpart, Virgo, have detected numerous events, including neutron star mergers. These mergers are particularly fascinating because they produce both gravitational waves and electromagnetic signals, such as gamma-ray bursts. By observing these signals together, astronomers can learn about the origins of heavy elements like gold and platinum, forged in the aftermath of such collisions. The existence of gravitational waves also has profound implications for our understanding of spacetime. They demonstrate that spacetime is not static, but dynamic, capable of carrying energy across vast distances. This realization challenges our traditional notions of a passive universe and suggests a more interconnected, vibrant cosmic fabric. One of the most exciting aspects of gravitational waves is their potential to reveal new physics. For instance, by studying how these waves interact with their environment, scientists hope to test theories about dark matter and quantum gravity. Gravitational waves might also carry clues about the earliest moments of the universe, offering a glimpse into the conditions just after the Big Bang. Looking ahead, the future of gravitational wave astronomy is bright. Plans are underway for more sensitive detectors, including space-based observatories like the Laser Interferometer Space Antenna, LISA. These instruments will expand our ability to detect waves from a broader range of sources, from supermassive black hole mergers to the gentle hum of gravitational waves produced by the collective motion of the universe. Gravitational waves have transformed the way we explore the cosmos. They are not just a confirmation of Einstein's genius, but a new tool for understanding the forces that shape our universe. As we continue to listen to these ripples in space-time, we uncover stories of cosmic violence, creation, and evolution, deepening our appreciation for the interconnected tapestry of existence. While the idea of curved spacetime is central to our understanding of the universe, there are regions where spacetime appears to be flat, or nearly so. These flat regions represent the baseline geometry of the universe in the absence of significant mass or energy. Understanding such areas not only deepens our grasp of spacetime's nature, but also raises fascinating questions about the structure and evolution of the cosmos. Flat spacetime, often referred to as Minkowski space, is the simplest solution to Einstein's equations of general relativity. It describes a universe without mass or energy, a hypothetical scenario where gravity plays no role. In such a region, space-time resembles a smooth, uncurved plane where the familiar rules of classical physics apply. Objects move in straight lines, and time ticks uniformly without the distortions caused by gravitational forces. In reality, perfect flatness doesn't exist. Even in seemingly empty regions of intergalactic space, small amounts of matter, energy, or dark matter create minute curvature. However, these regions are so sparsely populated that the effects of curvature become negligible, making them appear nearly flat from a practical perspective. These flat zones serve as laboratories for testing fundamental theories of physics, as their simplicity allows scientists to isolate and study the behavior of space-time without the complications introduced by gravity. Flat regions are crucial in understanding the larger structure of the universe. Cosmologists believe the universe on the largest scales is remarkably uniform and isotropic, meaning it looks the same in every direction. Observations of the cosmic microwave background radiation, the faint afterglow of the Big Bang, confirm this uniformity. However, these observations also suggest that the universe is nearly flat overall, with only slight curvature arising from its total mass-energy content. This near flatness has profound implications for cosmology. If the universe is flat, its geometry allows for infinite expansion, contrasting with the closed, curved geometry of a universe that might eventually collapse back on itself. Measurements from missions like NASA's WMAP and ESA's Planck satellite have refined our understanding of this flatness, showing that the universe's shape is astonishingly close to flat, but not perfectly so. This delicate balance raises questions about the early conditions of the cosmos. One explanation for this near flatness is cosmic inflation, a rapid expansion that occurred fractions of a second after the Big Bang. During inflation, the universe expanded exponentially, smoothing out any initial curvature. This process would leave the universe flat on large scales, much like how the surface of a balloon appears flat when viewed up close, even though it curves on a larger scale. Flat regions also play a role in quantum mechanics and the study of virtual particles. In a flat region of space-time, quantum fluctuations still occur, producing pairs of particles that briefly pop into existence before annihilating. These virtual particles can have measurable effects, such as contributing to the Casimir effect, where flat regions of space-time between closely spaced plates exhibit quantum mechanical forces. The concept of flat space-time extends into the realm of theoretical physics, particularly in discussions about alternate dimensions and universes. In some models, flat space-time serves as a boundary or framework for higher dimensional structures. For example, string theory suggests that our universe might exist on a flat brane embedded within a higher dimensional space. Despite its simplicity, flat space-time poses profound questions about the nature of reality. Why does the universe appear so close to flat, and what mechanisms maintain this delicate balance? Could flatness be an intrinsic property of space-time, or is it a transient state in the universe's evolution? Flat regions of space-time remind us that even in the vast emptiness of the cosmos, there is structure and order. These areas offer a glimpse into a universe where gravity's influence fades, allowing us to explore the fundamental nature of existence with clarity. They provide a counterpoint to the dramatic curvatures of black holes and cosmic events, highlighting the diverse and dynamic geometry of space-time itself. When space-time bends under the influence of massive objects, it forms a predictable geometry that defines the motion of matter and light. But what happens when space-time undergoes extreme distortions, to the point where it might rip or tear? Could the fabric of the universe break, creating bridges across vast distances or entirely new realms? These questions push the boundaries of our understanding and lead to some of the most speculative yet fascinating ideas in modern physics. The notion of space-time ripping is closely tied to the extreme scenarios predicted by Einstein's general relativity. Singularities, points of infinite density where the equations of general relativity break down, are a prime example. Found at the cores of black holes, singularities represent places where the curvature of space-time becomes infinite, effectively tearing the fabric of the universe. However, these singularities are hidden behind event horizons, shielding them from direct observation and keeping the rip contained. Singularities are not limited to black holes. Some cosmological models suggest that the Big Bang itself originated from a singularity, where all the matter and energy in the universe were compressed into an infinitesimally small point. This idea raises profound questions about the nature of time, space, and causality, as well as whether such singularities could form again in phenomena like the Big Crunch, a hypothetical scenario where the universe collapses back into a singularity. While singularities mark potential rips in space-time, the concept of wormholes suggests that these rips could connect distant regions of the universe. Wormholes, also known as Einstein-Rosen bridges, are theoretical shortcuts through space-time, linking two separate points in the cosmos. Imagine folding a piece of paper so that 2 points touch. A wormhole would be the tunnel connecting them. In theory, a wormhole could allow faster-than-light travel or even connect entirely different universes. Despite their appeal, wormholes face significant challenges. They are inherently unstable and prone to collapse unless stabilized by exotic matter, hypothetical material with negative energy density. No evidence for such exotic matter exists, and the practical creation or maintenance of a wormhole remains firmly in the realm of science fiction. Yet the idea continues to captivate scientists and storytellers alike, offering tantalizing possibilities for interstellar travel and exploration. Another extreme scenario involving space-time tears is the Big Rip, a hypothetical end-of-the-universe scenario driven by dark energy. If dark energy, the mysterious force causing the universe's accelerated expansion, grows stronger over time, it could eventually overcome all other forces, including gravity, electromagnetism, and even the nuclear forces binding atoms. In this apocalyptic future, galaxies, stars, planets, and eventually atoms themselves would be torn apart, leaving a universe devoid of structure. Even in less dramatic cases, extreme space-time distortions can lead to surprising effects. The edges of black holes, known as event horizons, represent a kind of boundary where space-time is stretched so severely that escape becomes impossible. Near these boundaries, space and time behave in ways that defy our intuition. Time slows to a crawl relative to distant observers, and light emitted from this region is redshifted to invisibility. Theoretical physicists have also explored scenarios involving naked singularities, singularities not hidden behind an event horizon. These would expose the raw, infinitely curved nature of space-time, potentially revealing new physics. However, most scientists believe in the cosmic censorship conjecture, which posits that nature prevents such singularities from being observed. On a more speculative level, some theories suggest that space-time could experience smaller-scale tears or disruptions at the quantum level. Quantum gravity, a yet undeveloped theory combining general relativity and quantum mechanics, might predict fluctuations or foamy structures in space-time at extremely small scales. Such quantum tears could have implications for the fabric of the universe itself, influencing phenomena from black hole evaporation to the birth of new universes. The concept of space-time ripping challenges us to think beyond the conventional framework of physics. It raises questions about the limits of the universe's structure, the possibilities for interstellar shortcuts, and the ultimate fate of the cosmos. Whether through the singularities of black holes, the hypothetical passages of wormholes, or the speculative endgame of the Big Rip, these ideas stretch our imagination and deepen our quest to understand the universe's most profound mysteries. The universe is not static. It is expanding, a discovery that fundamentally reshaped our understanding of space-time. This expansion is not merely the movement of galaxies through space, but the stretching of space-time itself, a dynamic and ongoing process that defines the evolution of the cosmos. Exploring the mechanisms and implications of this expansion reveals a universe in constant motion, shaped by forces both known and mysterious. The idea of an expanding universe was first proposed in the early 20th century, bolstered by Edwin Hubble's observation that galaxies are moving away from us, their light redshifted as they recede. This redshift is a direct result of the stretching of space-time, causing the wavelengths of light traveling through it to elongate. This discovery confirmed predictions made by Einstein's equations of general relativity, which allow for a universe that can expand, contract, or remain in a steady state depending on its energy content. The rate of this expansion is described by the Hubble constant, which measures how quickly galaxies are receding as a function of their distance. However, determining the precise value of the Hubble constant has proven challenging, with different measurement techniques yielding slightly different results. This Hubble tension is one of the major puzzles in cosmology today, hinting that our understanding of the universe's dynamics may still be incomplete. The expansion of space-time itself has profound implications. Unlike conventional motion, where objects move through space, the expansion of the universe means that space-time itself is growing. Galaxies are not flying apart due to an initial explosion, but are being carried along as the fabric of space-time stretches. This phenomenon allows the distance between objects to increase without them moving through space in the traditional sense. One of the most startling aspects of the expanding universe is its acceleration, driven by a mysterious force known as dark energy. Discovered in the late 1990s through observations of distant supernovae, dark energy accounts for approximately 70% of the universe's energy density. Its repulsive effect counteracts the gravitational pull of matter, causing the expansion of the universe to speed up over time. The nature of dark energy remains one of the greatest mysteries in modern science, with theories ranging from a cosmological constant, a fixed energy associated with space itself, to dynamic fields that evolve over time. The expansion of the universe also defines its large-scale structure. Over billions of years, regions of higher density have collapsed under gravity to form galaxies, clusters, and superclusters, while lower density regions have expanded, creating vast cosmic voids. These structures are mapped by the cosmic web, a sprawling network of filaments and clusters connected by the threads of gravity and stretched by the expansion of space-time. Another consequence of the expanding universe is the cooling and redshifting of the cosmic microwave background, CMB, radiation. This faint glow, the afterglow of the Big Bang, provides a snapshot of the universe when it was only 380,000 years old. As the universe expands, the wavelengths of this radiation stretch, cooling it over billions of years. Today, the CMB is observed as a uniform, low-energy signal, offering a window into the conditions of the early universe and the seeds of cosmic structure. The stretching of space-time also limits how much of the universe we can observe. Light from distant galaxies takes billions of years to reach us, meaning we see them as they were in the distant past. However, as the universe expands, some regions recede faster than the speed of light due to the stretching of space-time, placing them beyond our observational reach. This creates a cosmic horizon, a boundary beyond which we can never see, shaping our understanding of the universe's scale and history. The expanding universe is more than an abstract concept. It shapes every aspect of cosmology, from the behavior of galaxies to the ultimate fate of the cosmos. If the acceleration driven by dark energy continues indefinitely, the universe will experience a big freeze, where galaxies drift apart, stars burn out, and the cosmos grows dark and cold. Alternatively, if dark energy changes over time, other outcomes, such as a big crunch or big rip, become possible. The stretching of space-time is a testament to the dynamic nature of the universe. It reminds us that the cosmos is not a static entity, but an ever-evolving tapestry shaped by forces both visible and hidden. By studying the expanding universe, we not only explore the nature of space-time, but also confront the deepest questions about the origins, evolution, and destiny of existence. Quantum mechanics and curved space-time occupy two seemingly distinct realms of physics. Quantum mechanics governs the tiny world of particles and forces at subatomic scales, while curved space-time is the domain of general relativity, describing the warping of the universe by massive objects. Reconciling these two frameworks remains one of the most profound challenges in modern science. Yet their interplay reveals a universe rich in complexity, where the smallest scales influence the largest and vice versa. At the heart of the tension between quantum mechanics and curved space-time is the fact that quantum phenomena operate within the fabric of space-time itself. Particles, waves, and fields exist and interact within this dynamic stage, but they also influence it. Einstein's equations show how energy and momentum curve space-time, and quantum systems possess energy, even in their empty states. Consider the vacuum of space. In classical physics, a vacuum is devoid of matter and energy. Quantum mechanics, however, reveals that even a perfect vacuum teems with activity. Virtual particles, temporary fluctuations of energy, pop in and out of existence, contributing to what is known as the vacuum energy. This quantum activity, present even in the emptiest regions of the universe, plays a role in shaping the curvature of space-time. One striking manifestation of this interaction is Hawking radiation, a phenomenon predicted by Stephen Hawking in 1974. Near the event horizon of a black hole, quantum effects come into play. Pairs of virtual particles form at the edge of the horizon, and one particle falls into the black hole while the other escapes into space. This process causes the black hole to lose mass and energy over time, eventually evaporating entirely. Hawking radiation demonstrates how quantum mechanics influences even the most extreme curvatures of space-time, providing a glimpse into the elusive connection between these two realms. Another arena where quantum mechanics meets curved space-time is in the early universe. During the moments following the Big Bang, the universe was an incredibly dense and hot singularity, where quantum effects governed the behavior of particles. This era, known as the Planck epoch, is a region of space-time where both quantum mechanics and general relativity are required to describe reality. It is here that a unified theory of quantum gravity is most urgently needed, as neither framework alone suffices to explain the conditions of the nascent cosmos. Quantum mechanics also provides insights into the structure of black holes. The information paradox, one of the most famous puzzles in theoretical physics, arises from the apparent conflict between quantum mechanics and general relativity. According to quantum theory, information about a system cannot be destroyed. However, when a black hole evaporates via Hawking radiation, it seems to erase all information about the matter that fell into it. Resolving this paradox could offer critical clues about the quantum nature of spacetime. Efforts to bridge the gap between quantum mechanics and curved spacetime have led to several promising theoretical frameworks. String theory, for example, proposes that particles are not point-like objects, but tiny, vibrating strings whose modes of vibration correspond to different particles. String theory incorporates both quantum mechanics and general relativity, suggesting that spacetime itself may emerge from more fundamental quantum entities. Another approach is loop quantum gravity, which reimagines spacetime as a network of discrete loops rather than a smooth continuum. In this model, spacetime is granular at the smallest scales, with quantum effects influencing its structure. This discretized view of spacetime offers potential resolutions to problems like singularities, where classical general relativity breaks down. Even more speculative ideas include the holographic principle, which suggests that the information contained within a region of spacetime can be described entirely by a lower dimensional boundary. This principle, inspired by black hole thermodynamics, implies that spacetime itself might be a projection of more fundamental processes occurring at the universe's edges. Quantum mechanics and curved spacetime also intersect in the study of gravitational waves. The detection of these ripples in spacetime has opened a new window for probing the quantum nature of gravity. Experiments at the intersection of quantum technologies and gravitational wave observatories may one day uncover evidence of quantum effects influencing the fabric of the cosmos. While the union of quantum mechanics and curved spacetime remains elusive, their interplay is not just a challenge, but an opportunity. Each step toward reconciling these frameworks brings us closer to understanding the true nature of the universe. The mysteries of quantum gravity invite us to think beyond our current paradigms, exploring a reality where the very fabric of existence is shaped by the interplay of the smallest particles and the vastest curvatures. Visualizing spacetime curvature is one of the most intriguing challenges in science communication and astrophysics. Spacetime, a four-dimensional continuum, is invisible to the naked eye and beyond direct sensory experience. Yet scientists and educators have developed ingenious ways to represent its dynamics, helping us comprehend how massive objects warp the fabric of the universe and influence everything within it. One of the most common ways to illustrate spacetime curvature is through the rubber sheet analogy. Imagine a flexible sheet stretched taut, representing the fabric of spacetime. When you place a heavy object like a ball on the sheet, it creates a depression. Smaller objects, like marbles, roll toward the heavier object, mimicking how planets and stars follow the curves created by massive bodies. While this analogy is limited, it represents two-dimensional space warped into a third dimension. It effectively conveys the idea of gravity as a result of curved spacetime rather than an invisible force. Modern tools like computer simulations and animations take this analogy a step further. Advanced models use 3D renderings to depict how massive objects stretch and warp spacetime in all directions. These visualizations often represent time as an additional axis, creating dynamic, flowing depictions of how events unfold in spacetime. For instance, simulations of merging black holes show the ripples of gravitational waves propagating outward, distorting the grid lines of an imagined spacetime framework. One striking visualization is the depiction of gravitational lensing. When light from a distant object passes near a massive body, the curved spacetime around the body bends the light, creating arcs, rings, or multiple images of the same source. Scientists illustrate this phenomenon using colorful overlays and animations, highlighting how the invisible curvature of space-time dramatically alters our perception of distant galaxies. To represent extreme curvature, such as near black holes, artists and physicists often use simulations that depict light paths and orbital motion around these cosmic behemoths. The famous first-ever image of a black hole shadow, captured by the Event Horizon Telescope, is a practical example of visualizing space-time in action. This image reveals the glowing ring of light around the event horizon, distorted by intense gravitational lensing. Another powerful way to visualize space-time is through gravitational wave simulations. These ripples in the cosmic fabric, generated by events like black hole mergers, are illustrated as expanding rings or undulating waves that stretch and compress space-time. LIGO and Virgo's detections of these waves are often represented as oscillating curves or heat maps, making their subtle effects comprehensible. Even the structure of the universe itself, the cosmic web, is a visualization of space-time on the largest scales. This intricate network of filaments, clusters, and voids, revealed by simulations and observations, shows how gravity shapes the distribution of matter across billions of light years. These visualizations often use vibrant colors and high-resolution mapping to highlight the interconnectedness of galaxies and dark matter within the cosmic tapestry. To illustrate the bending of time, scientists use graphs and space-time diagrams that plot events in a four-dimensional framework. These diagrams often depict how time slows near massive objects, a concept known as time dilation. For example, a clock near a black hole would tick more slowly than one farther away, and space-time diagrams visually represent this distortion by stretching or compressing the time axis. Emerging technologies like virtual reality, VR, and augmented reality, AR, are taking space-time visualization to new heights. VR simulations allow users to step inside a black hole or explore the warping of space-time around massive objects, offering an immersive experience of concepts that were once purely abstract. AR applications overlay space-time distortions onto real-world environments, making the invisible geometry of the universe tangible and interactive. Beyond scientific tools, artists and filmmakers contribute to visualizing space-time in ways that engage the imagination. Movies like Interstellar use scientifically informed depictions of black holes and wormholes to bring complex concepts to the screen. The black hole gargantua, for instance, was modeled using equations from theoretical physicists, resulting in a depiction that remains one of the most accurate in popular media. Visualizing space-time curvature isn't just about creating beautiful images. It's about making the abstract accessible and igniting curiosity about the universe. These representations bridge the gap between complex mathematical theories and human understanding, showing us the profound interconnectedness of space, time, and matter. Dark matter and dark energy are among the most enigmatic components of our universe, shaping the curvature of space-time and influencing its evolution in ways we are only beginning to understand. Together, they account for approximately 95% of the universe's total energy density, yet their true nature remains elusive. Exploring how these mysterious phenomena interact with space-time reveals a cosmos far stranger than we ever imagined. Dark matter is a form of matter that does not emit, absorb, or reflect light, making it invisible to telescopes. Yet its presence is unmistakable due to its gravitational effects. In the 1930s, astronomer Fritz Zwicky observed that galaxies in the Coma cluster moved as if under the influence of far more mass than could be accounted for by visible stars and gas. Decades later, studies of galactic rotation curves showed that stars in the outer regions of galaxies orbit faster than expected, suggesting the presence of a vast halo of unseen matter. Dark matter's influence on space-time is profound. It shapes the gravitational wells in which galaxies and galaxy clusters form, contributing to the large-scale structure of the universe. Without dark matter, the observed distribution of galaxies and cosmic filaments would be vastly different, as visible matter alone lacks the gravitational pull to create these structures. Simulations of cosmic evolution, incorporating dark matter, reproduce the intricate web of clusters and voids observed in the universe today. Despite its critical role in shaping space-time, The exact composition of dark matter remains a mystery. Leading candidates include weakly interacting massive particles, WIMPs, and axions, hypothetical particles that interact weakly with normal matter. Alternatively, some theories propose that modifications to our understanding of gravity could account for the effects attributed to dark matter. Until direct detection is achieved, dark matter remains one of the most tantalizing puzzles in astrophysics. Dark energy, on the other hand, is even more mysterious. It was discovered in the late 1990s when observations of distant supernovae revealed that the universe's expansion is accelerating. This unexpected finding suggested the existence of a force counteracting gravity on cosmic scales, pushing galaxies apart. Unlike dark matter, which pulls matter together, dark energy exerts a repulsive effect, stretching space-time itself. The simplest explanation for dark energy is the cosmological constant, a term in Einstein's equations that represents the energy density of empty space. This concept aligns with the idea that space-time has an intrinsic energy, causing it to expand. However, the exact value of the cosmological constant is puzzlingly small compared to predictions from quantum field theory, raising questions about its origin and nature. Another possibility is that dark energy arises from a dynamic field, such as quintessence, which evolves over time. In this scenario, the effects of dark energy could change, potentially altering the universe's fate. Observations of the cosmic microwave background and large-scale structure aim to distinguish between these possibilities. But for now, the true nature of dark energy remains uncertain. Dark energy's influence on space-time curvature is dramatic. It dominates the energy budget of the universe, accounting for roughly 70% of its total density. As dark energy drives the accelerated expansion of space-time, it increases the separation between galaxies, effectively isolating them over vast distances. If this expansion continues indefinitely, it could lead to a big freeze, where galaxies drift so far apart that the universe becomes cold, dark, and lifeless. On even larger scales, the interplay between dark matter and dark energy determines the ultimate geometry of the universe. If dark energy's effects intensify over time, it could lead to a big rip, tearing apart not only galaxies but also stars, planets, and eventually atoms themselves. Alternatively, if dark energy diminishes, gravitational forces could cause the universe to reverse its expansion, collapsing into a big crunch. The influence of dark matter and dark energy on space-time is also evident in phenomena like gravitational lensing. Dark matter's gravitational pull bends light from distant galaxies, creating arcs and distortions that reveal its distribution. These lensing effects provide a way to map dark matter's presence, even though it is invisible. Similarly, dark energy's effects are seen in the accelerating motion of galaxies, which require sophisticated models of space-time to describe. As scientists probe these mysteries, new tools and experiments offer hope for breakthroughs. Next-generation observatories, such as the James Webb Space Telescope and the Euclid mission, are poised to study the effects of dark matter and dark energy on space-time with unprecedented precision. Particle physics experiments aim to detect dark matter particles directly, while cosmological surveys seek to refine our understanding of dark energy's influence. The mysteries of dark matter and dark energy remind us of the vast gaps in our understanding of the universe. They reveal a cosmos where the visible is just the tip of the iceberg, and where unseen forces shape the very fabric of reality. By exploring their influence on space-time, we take one step closer to unraveling the profound secrets of existence. If you liked the video, don't forget to subscribe to the channel. This helps my work a lot and shows me that you are interested in me continuing to produce more videos.